A new polymer follows the Kelvin model. The quantity eta viscosity obeys the WLF equation and E obeys rubber elasticity theory. The glass transition temperature of the polymer is 5 degrees centigrade, where it has a viscosity of 10 to the power 13 poises. The concentration of active chain segments is 10 to the negative 4 moles per centimeter cube. The temperature of the experiment is 30 degrees centigrade. How does this polymer creep with time under a stress of 10 to the power 7 dynes per centimeter squared? A plot of strain versus time is required. Briefly discuss two ways to slow down or reduce the rate of creep in part A. Knowing the viscosity at 5 degrees centigrade, which is the glass transition temperature, we can find out the viscosity at 30 degrees centigrade, which is the temperature of the experiment, using WLF equation. Knowing the concentration of active chain segments, we can find out the modulus at 30 degrees centigrade. So with the value of viscosity and modulus at 30 degrees centigrade, we can find out the strain for the Kelvin model. Let's first start with the WLF equation. Log eta over eta g, where eta g is 10 to the power 13 poises, equals negative 17.44 times T minus Tg, which is 30 minus 5, divided by 51.6 plus T minus Tg again. This is the value of eta we are getting. Now, for the modulus, E equals 3n RT, where n is the concentration of the chain segments. So 3 times 10 to the negative 4 moles per centimeter cube times R is 8.31 times 10 to the power 7 ergs per mole per Kelvin times 303 Kelvin. 7.56 times 10 to the power 6 dynes per centimeter square. For a Kelvin model, we have a spring and dashpot in parallel. So, the stress is different for the spring and the dashpot, but the strain is the same. The strain is given by sigma over E times 1 minus exponential minus Et over eta. Plugging in the values, sigma over E equals 10 dynes per centimeter square divided by 7.56 dynes per centimeter square, which is equal to 1.323. E over eta equals 7.56 times 10 to the power 6 dynes per centimeter square over 2.03 times 10 to the power 7 poises, 0.372 per second. So plugging in, we can see that 1.323 times 1 minus exponential minus 0.372 t. We can now plug in the various values for time in this equation to get the values of strain. So if we plot the graph, Part B, the question is, briefly discuss two ways to slow down or reduce the rate of creep in part A. The rate of creep would be the slope of this curve. So we can say dou epsilon by dou t equals sigma over eta times exponential minus e t over eta. Decrease rate of creep, we can see that we have to decrease stress or decrease sigma or increase modulus. Eta is complicated because you have sigma over eta and as well as you have exponential minus et over eta. So two ways to decrease rate of creep would be decrease the stress and increase the modulus.